We looked at the geometry of the Earth, Moon, Sun system. We've also looked at the motion of the stars, seasonal constellations, and things like that. And they were well known and predictable in ancient times. In fact, predicting the motion of these objects was an important skill for ancient peoples, particularly things like navigational purposes. So using the stars to navigate around the planet, particularly on the oceans, was very, very useful. Using the motions of these objects to predict the seasons. So studying how the sun behaved over the course of the year, or how the different constellations appeared throughout the course of the year, was very, very useful. Particularly whenever humans have gone from being hunter-gatherers to being farmers. With the birth of what we call civilization, this is a very, very important tool. In fact, there are astronomically aligned buildings all over the world which are designed specifically for that purpose. One of the most famous ones is recorded here. It's a picture of it at Stonehenge in the southwest of England. The site has been used for almost 10,000 years. The stone circle that you see in evidence today is the latest incarnation, but we have it dates around about 4,000 years ago. But certainly there's evidence that people were working on this site for well over 1,000 years easily. And it still does the purpose for which it was originally intended. If you're looking from inside the center of the stone circle, on the longest day of the year, the summer solstice, the sun appears to rise in the morning above this stone, which is called the heel stone. And it still does today. In fact, there are festivals that you can see even going on today on the day of the summer solstice. I would definitely recommend, if you get the chance to go there, I definitely recommend that you do so. I've taken students several times to Stonehenge. This group went in 2007. The visitor centre has been renewed today, and it's really quite an impressive sight, although it does have an eerie feel to it, especially whenever you see crows and things flying around. It definitely has an eerie luster to it, even though you can see some scary things. Like that looks like an image of a person there in the background. But I definitely recommend, if you get the chance, to go and visit it. The motion of the planets, though, has been much more difficult to predict. So there are 5 objects which move around the nighttime sky that you can see with the naked eye. And ancient peoples had a terrible time trying to figure out exactly the motion of these objects and how they behaved, and being able to try to predict where they were in the sky. Ancient people saw those 5 objects and the sun and the moon as gods to be worshipped. In fact, that's the only reason why we actually have 7 days to a week today. We have days named after every one of these supposed gods. Some of them are easy to work out, like Sunday and Monday are definitely named after the sun and the moon. Saturday obviously named after Saturn. Other ones are not so easy to pick out. Tuesday is named after Mars. The Roman god Mars has a Germanic equivalent, Tu. So there's where Tuesday comes from. Wednesday is named after Mercury. If you look at it in French, or if you look at it in Spanish, the word definitely sounds much more like Mercury. The Roman equivalent of Mercury in the Germanic gods is called Woden, so that's a Woden's Day or Wednesday. Thursday or Thor's Day is named after the planet Jupiter. Jupiter and Thor are equivalent. And Friday is named after the planet Venus. The goddess Venus has a Germanic equivalent called Freya, which is where Friday comes from, Freya's day. And these objects were called planets. It comes from the Greek word meaning wanderer. They appeared to move around the sky in a random fashion, and it was very, very difficult to predict their motion. Certainly they could study it over a long period of time and see the motion, but trying to figure out why it was doing, the planets were doing the way they were, was difficult to work out. If they move across the sky in the same direction as the sun, that is known as prograde motion. That's from west slowly across the sky towards the east, and if it goes in the opposite direction, then that's known as retrograde motion. And it was the retrograde motion of these planets which was very, very difficult to predict. Now, if you look at the planets from the perspective of the Earth, you can divide them up into two types. There are inferior planets. Those are ones that are closer to the Sun than we are. And there are superior planets. Those are planets which are farther away from the Sun than we are. So the inferior ones are Venus and Mercury, and they definitely behave differently from the rest of the planets because they never get far away from the Sun. You'll only ever see Venus or Mercury in the evening sky or in the morning sky. You'll never be able to see them in the sky at midnight. It's just not possible for that to happen. Whereas the planets like Mercury and Saturn, the outer planets, the superior planets, they can be completely opposite the Sun in the sky, so you can see them at any time of the day or the night. Now, the reason why Venus and Mercury never get far away from the Sun is because we're further from the Sun than they are. They're linked closely to the Sun, and so they never get far away. In fact, when you're hunting for them, you're always either looking for them in the morning sky or the evening sky. So here's an image that I've taken from Stellarium showing you how you would pick up Venus as an evening star. It's called the evening star because it's far brighter than the rest of the objects in the sky. In fact, the brightest object is the Sun, then you've got the Moon, and then the next brightest object is Venus. So as the Sun sets and the sky begins to get dark, Venus is typically the first thing that you can see, which is why it's sometimes called the evening star. So here we have just after 40 minutes after sunset, and there's Venus in the sky, even before some of the rest of the stars are appearing. So it never gets far away from the Sun. Mercury, because it's closer to the Sun, is even more difficult to pick out. In fact, over 20 years of searching for Mercury in the sky, I've only ever been convinced less than 10 times that what I'm actually observing with the naked eye is definitely Mercury. Here's another image taken from Stellarium. This time it's looking into the morning sky, and this is only 20 minutes before sunrise. And you can just about pick out Mercury before the Sun comes up. Now, if you're a planet hunter and you're chasing for these elusive objects, Venus is easy enough to pick out, but Mercury is very, very difficult. It can be very, very dangerous if you're looking for them at western elongation, because that is in the morning time, as opposed to eastern elongation, which is in the evening time. Because you know that once the Sun sets in the evening, it's not going to come back up again, so you could scan the horizon with a pair of binoculars looking for Mercury. Whereas in the morning time, the Sun could come up at any moment, and if you're scanning around in the vicinity of the Sun with a pair of binoculars, that could be extremely dangerous. They're usually very, very difficult to pick out in the sky. Oftentimes, though, you can be helped. Here is Mercury, which you can pick out and identify because it's very, very close to the Moon in the sky. So sometimes it's easier than others to pick it out. Or if you have the benefit of a total eclipse of the Sun, here's an image taken of the Sun during totality. In fact, you can still see there is daylight off in the distance in this particular image. But what's happened here is the Moon has gone in front of the Sun, so you can see the solar corona, the crown of the Sun, as the Moon has blocked it out. So the Sun's during an eclipse, and now you can begin to see the other objects in the sky because the sky's dark and you can pick it out. There is Mercury, which is easy enough to identify. And there's Venus, which is definitely easy to identify during a total eclipse. But they never get far away from the Sun, so much more difficult to pick out than the other planets, because they're usually seen in the glare of the Sun. Because they orbit the Sun closer to the Earth, they go through all the phases that you can see, similar phases to what we've already talked about in terms of the Moon. In the top right here you can see a video image showing you how Venus will go through all the phases. And there's a massive difference in the actual distance from the Earth to the Moon, and so when it shows a thin crescent phase, it's usually a very, very large crescent, and when it shows a full phase, it's usually a way off in the distance. Now, a superior planet can never show these crescent phases that you see, so there's a definite difference between an inferior planet than there is to a superior planet. In fact, it was Galileo, when he first pointed a telescope at Venus and could see the different phases that Venus went through, that he was convinced that the heliocentric model of the solar system, the Copernican model, was the correct model. On the next slide you can see how those phases change dramatically over the course of months, because the distance to Venus is changing quite dramatically. And I can represent that to you if I put the Sun at the center of the solar system, and then I'll draw in the orbit of the Earth, and then the orbit of Venus is like that. And you can see how from the Earth's perspective the distance to Venus changes quite dramatically. So there's the Earth, and then Venus, when it's at its closest approach, would be in position 1, I'll call that V1, and then Venus, when it's at its farthest distance, I'll call that V2. So the distance from the Earth to the Sun is 1 astronomical unit. The distance from Venus to the Sun is 0.7 astronomical units. And so you can see there that the closest approach would then be 0.3 astronomical units, and then the farthest distance from the Earth to Venus would be 1.7 astronomical units. That means that there's essentially a 600% difference in the size of Venus in the sky. So whenever it's far, far away, it's about 6 times smaller than when it's up close, at its closest approach to the Earth. So there's a massive variation there, but it essentially means that Venus pretty much, the variation in brightness changes, but it doesn't change by that much, because when it's really, really close, we can only see a tiny little sliver of the lit up side. When it's far away, we can see it's a lot smaller, but we can see a much, much bigger phase.